Another reaction that we can do with alkenes is a dihydroxylation, which, if you can imagine, is adding two hydroxyl groups across a double bond. This is ethylene glycol, which is in antifreeze. It has a sweet taste. So a dihydroxylation is addition of two alcohols across a double bond. If we add peroxy acid across a double bond, we first form an epoxide. Water and acid is then added to that. To form a trans-diol, plus the enantiomer. So the trans is because the alcohols are doing an anti-addition. And the diol is from the two alcohols. This is a multi-step process. In the mechanism here, which you do not need to know, the alkene will attack the oxygen of the peroxy acid. This electron pair comes in to form a double bond. This one grabs the hydrogen. These electrons go onto there. So I'm going to draw the transition state. So these are all the things that are happening. So this bond here forms, this one here forms. So I get the epoxide plus the R. So I have a carboxylic acid as the side product. Once the epoxide is formed, acid is present. Can do a proton transfer. So that gets protonated. We have this oxonium. Waters are nucleophile, and here we have an electrophilic or two partially positive areas. So we'll get a nucleophilic hug. And that will come from the bottom side as well because of sterics. And then we have the OH here. Another proton transfer. So this is an anti-diol plus the enantiomer. If you remember, water is not a very good nucleophile here, which is why we have to add that acid to make the electrophile better. One thing that we've seen in common is these three-membered positive rings. There's lots of ring strain here. So they're good electrophiles, and they yield anti-products. The anti-products are due to the nucleophile attacking from the opposite side of the leaving group. So this is considered the leaving group. This is the leaving group and the leaving group here. If we want to perform a Syn dihydroxylation, we use a different reagent. This is OSO4, or osmium tetroxide. This goes through what is called a cyclic osmate ester. In one step form, we can use a weak base or Na2SO3 in order to remove the osmate part. So we end up with the Syn diol. You can use NMO or terpbutyl peroxide to remove the osmate ester. All of those will give you the Syn diol. This is 60 to 90%. You can also use potassium permanganate, or KMNO4. This is an intermediate that is not isolated. Once we add sodium hydroxide to that, you get the diol in 85% yield. So this guy is expensive, which is why we might want to use the KMNO4, and you can use milder conditions. So a couple of problems. Br across the double bond. I'm going to exclude stereochemistry here. We get Br2 plus water. We're going to form the bromonium, and the water is smaller than the Br, so that will sneak in here to the more substituted position. And then we get the Br. With the peroxy acid and water, we first form the epoxide. And then we get the diol. And with OSO4, we get a Syn diol. We can do oxidative cleavage reactions. In an oxidative reaction, this occurs with ozone, and this process is called ozonolysis. You have likely smelled ozone before if you have stood next to a copier. That distinct smell is the smell of ozone. And what this does is it cuts the double bond in half, and you can imagine separating it or pulling them apart. So I'm going to cut them in half and pull them apart, and that will add oxygen in its place. So here we end up with a ketone and an aldehyde. So this requires ozone followed by dimethyl sulfide. I will show you a brief mechanism. The nucleophilic alkene can attack this oxygen, which is electrophilic. Those electrons come into here. This electron goes to here. So we form what is called an ozonide. This is an ozonide. And the electrons shift again. This bond here breaks to form the carbonyl double bond. These go on to the oxygen, and the lone pair electrons come in here to form the double bond. So we get the two ketones there. So once that ozonide is formed, you really do need that mild reducing agent to get you the two ketones. For these reactions, again, we're just going to cleave the double bond. So I'm only cleaving that double bond, so there's that. I'm just going to count my carbons to make sure I have the right number. 2, 3, 4, 5. And then I put oxygen in its place. With OSO4, we're going to get the Syn diol plus the enantiomer. So all of these reactions we can use in our toolbox for doing syntheses. And when you're looking at syntheses, the first thing we want to try to figure out is one-step synthesis. So what reagent do I need to go from here to here? Or what type of reaction is happening? If I go from an alkene, and I'm adding two things here, this is an addition reaction. If I go from X to Y, this is substituting one group for another, so this is a substitution. So we're going to look for some sort of SN1 or SN2 reaction. And here X is done away with, and there's an alkene in its place, so we're doing an elimination reaction. So E1 or E2. If you start with this alkene here, there's a reaction that we're trying to do to get an alcohol, and there's a reagent that we can use to get a bromine and an alcohol. So a couple of things to notice about this. We have first is addition of alcohol. And it's the Markovnikov product. So the OH is on the more substituted carbon versus this two positions here. There's two ways that we have to add an OH with the Markovnikov product. The first is this just acid and water. That one goes through a carbocation, and I don't have to worry about a rearrangement because this is tertiary, so that one would work. If you did have to worry about a rearrangement, you could use the mercury. In this reaction here, you actually don't have any tools to get this exact regioselectivity, so we can't do this one. If you were thinking of doing the halohydrin, that would give you the wrong regioselectivity. The alcohol goes to the more substituted, so we can't do this one. But if we try to do this problem now, this is a multi-step synthesis, and I have a bromine at the secondary position, and it needs to move to the tertiary. We don't have any reactions where it can just skip from one to the other. But if I think about doing an elimination, that gives me a double bond, and then I can make ER add to the more substituted or the Markovnikov product. So this would be elimination. This is addition, and that would get me here. So this is not a one-step reaction. We have to combine steps. We can first do an elimination to get this, and then we can think about what reagents that we can use in order to do that. If I start with the bromine at the secondary, I use sodium methoxide. This is a small base. I will get an E2 elimination, or the Zaitsev product. If I use a big base, I'm going to get the Hoffman product, or the less substituted. So I want to make sure I use the correct reagents. So once I have my elimination here, I can add HBr and get the bromine put in the right spot via an addition reaction. If I want to make this alcohol, this is kind of a similar process where we have the alcohol going from tertiary into shifting over one carbon. The strategy again is to do an elimination. If I can eliminate it this way, then I can add water to get this. So this is an anti-Markovnikov product. We want to note that, and this is also a Hoffman elimination. So in going to our elimination, we want to get rid of the OH. We have to remember that OH is not a good leaving group, so we have to make it a better leaving group. And then we get that. When we do our elimination, we have our leaving group. We want to use a bulky base to get the less substituted product. And then once we have that, we need to add water to give us an anti-Markovnikov product. And the only reagent that we have that does that is the BH3, THF, OH-, and then the peroxide. And so that's how we can think about doing multi-step synthesis.